Good morning. I sat listening to the last two speakers, and I have to say, awesome speakers, tremendous amount of knowledge and a tremendous amount of work. But they're all both talking about the problems of PEM electrolyzers, the problem of membranes, and the problems that the industry has still got to face in terms of coming over some of the issues. Just imagine if you didn't have any of those problems. Clean Power Hydrogen. I had the great honor of running a business called Clean Power Hydrogen. We make electrolyzers without membranes. So we don't have any of those problems and any of the issues that people have spoken about before. We think it's fairly unique. It's got our IP on it. We got it patented. It's been going for quite a long time. The company's been going for 12 years plus. A lot of that is actually in development, in making sure it's scalable, sustainable, and safe. And we're very proudly based in the north of England in a place called Doncaster. And really, as a business, we want to strip everything back to make sure that our technology is firstly simple. If something is simple, it tends to be replaceable, and you can actually grow it. It has to be safe. That starts from day one of the company. Everything we do is leading towards making sure that we can put units on people's sites that is 100% safe and truly sustainable. About 98% of all our components are absolutely reusable, recyclable, and can be reused again. So what is it? It's a membrane-free electrolyzer. That's one that's actually been tested now. That's in our test center in Doncaster, and that's about to go to a customer's site. So how does it work? Electrolysis is electrolysis. That's the easy bit. But it's basically we take potable water, put it into a very, very simple stack. The stack is made from ubiquitous materials, which is basically just stainless steel. And we then separate the water into its components parts at the stack. That creates a mixed gas. So we are not separating the gas at the stack. We do that later on through cryogenics. So the cryogenics is just the science of cold, where we take the temperature down to minus 200 degrees, and the oxygen is distilled and becomes a liquid, and the hydrogen stays gaseous. And that's just a design of a 1 megawatt system. So very simply, to take it through pictorially, potable water goes into a very, very simple stack. The stack is just plates of metal. It then goes through a drying system. We have to take it to a very, very low dew point to make sure all moisture is out of the gas. The gas, in its very nature, is slightly moist. So we put it through two dryers, and they just regenerate. When one's wet, it dries out, and the other one switches over. Then it goes into the cryogenic system. That cryogenic system is fundamentally a great big sort of vacuum flask with liquid nitrogen in it, and then you get the mixed gas stream coming in, and then the oxygen goes out of one side, hydrogen goes out the other. On its own, that would be fairly the amount of power used in that on its own would require quite a lot, and it would be quite parasitic. We recycle about 95% of the cold energy. We have a heat exchanger in the top of that cryogen, meaning that we're recycling that cold energy that makes it very efficient. So you don't need massive cryo coolers. On the end of it, we basically have a nitrogen cryo cooler, which just pumps around and boils. Any boiled off nitrogen is then put back in and recooled. Oxygen comes out as very pure. Because it's distilled, it is pure, has no sort of cross-contamination in it whatsoever. And the hydrogen comes out at very high purity. It will come out at about 99.9, something like that. The very last bit, to get it to 5 nines, we put a deoxo dry on the end if it needs to be 5 nines. Although we believe that actually having a small amount of oxygen in the hydrogen at the end would actually be beneficial to fuel cell users. So that's how the technology works. We think it's good. We think it is disruptive. We spent a lot of time making sure that it's right. The features of the unit really are they're there on the left-hand side of the graph for you. It's the benefits really that for the consumer that are important. The cost of building this is less, and the reliability is improved. We have no platinum group metals, no iridium in it whatsoever. So we're not digging stuff out of the ground that is getting ever more costly and will run out. In terms of environmental benefits, it is just potable water. There's very little grey water at the end of it, and we don't need massive amounts of water for cooling. And as I say, it's completely recyclable, most of it. If a stack ever has to be reformed, we can take the stack out, reform it, put it back in again. And as I say, we believe the OPEX in terms of the lifetime cost of one of these units will be less than anybody else's. It is a competitive marketplace. We're not here to take all of the market. We recognise there are other people in the marketplace as well. But one thing, if I just slip back one slide, that stack, you can see the cell, one cell there, 2 plates, a gasket, and a sealant. That's it for a cell. So that's how complicated our member, the stack is, versus the complication of other stacks of competing technologies. So that's where we believe our greatest benefit is in terms of efficiency, in terms of use, in terms of reliability. And as a business, we're about to start our commercial journey. We have the first commercial units going out this year. We want to be a manufacturer of these units, but also, more importantly, we will also license it. So we have a dual strategy to build ourselves, which we'll do in the UK. But actually, these are best built where the demand is. There's no point building them all in the UK and trying to ship them around the world. You may as well build them where the demand is. So therefore, we have a licensing strategy to be able to license out the technology to whoever we agree with. And we currently do have 2 licenses already signed, and production is going to start of those fairly quickly. That means we can scale. Quickly. We have existing partners. One of our partners is a company called Fabrum, and they're a New Zealand-based company. They actually provide our cryogenic systems, the cryo coolers. They're starting to build a unit now down in New Zealand, and they will look after the New Zealand and Australian market. We have a partner in Germany and Scotland called Kase Deutad, who have a division called Kinera. They're an oil and gas services business and engineering business, and they're going to start production in a place called Bad Bentheim in Germany, and we'll look after sort of the North European market and some of the Middle East as well. And once we get those 2 licensed partners up and going, we'll also then start to look elsewhere once we know that we can get the supply chain built up and we have everything secured from that perspective. As I say, Kinera is a large business. They know how to do manufacturing. They've done it for an awful long time. They're also an investor in our company. We IPO'd the company on the London Stock Exchange 2 years ago, and Kinera are one of our key investors. And that's a picture of the other partner, Fabrum. They're actually on a stand next to us in the hall today, so please go and see them. And that's one of the electrolyzers that they're building down in Christchurch in New Zealand, which is going in the South Island. More than just being a license holder, they're also a partner in terms of developing our technology as well. And we have a very close relationship with Fabrum. And that's us. We think it's pretty special. We think we've got something that is got worldwide application. And we believe we want to create a legacy, and we want to create something that is good, and we're well on the way of doing it. So, thank you very much. There is a few minutes for questions if people want questions. If not,
Hi, Jon. Thanks. You've got to love the simplicity. What's the risk in mixed gas? If you
mixed gas is risky. Mixed gas is absolutely risky.
How do you sort of mitigate that?
And as I said at the start, we started the business from day one thinking about safety. First of all, you get rid of all ignition source. So you design it so there's no ignition source. Secondly, you then put in layers of protection that are funny enough. One of the speakers earlier was speaking about layers of protection. Massive layers of protection all the way through from a system perspective and controls perspective. So you have all those layers in terms of high highs and low lows and whatever else, and the machine completely will turn itself off if anything goes slightly amiss. And then thirdly, you then actually make sure even if it does get past all of that, it's all capable of being contained. So the work we put in terms of safety is enormous.
Have we got another? This gent.
So how many kilowatt per kilogram of hydrogen?
The first units are going out this year. Once we've done all the long tests and whatever else, we'll be able to publish that. But we believe the first ones will go out at about 58, 59 kilowatts per kilo. We think actually with R&D and improvements and as we scale, we can probably get that down to heading towards 50. That's the aim, but that's probably, that's an R&D project.
Where are we going to see the first of these in operation?
They're this year. This year. Okay. Brilliant. Thank you.